Hello, I am Brendan, and I am thrilled to have you here as we dive into the world of network automation architecture. Throughout this book, I will be popping in to introduce each chapter and wrap things up. But for the main narration, I'm handing over to the professional voice of Archird. We are starting with a reality check. Automation is powerful, but without the right structure, it is also dangerous. Let us join Archird for Chapter 1. Why brilliant automation gets shut down.
Chapter 1: Why brilliant automation gets shut down and how to prevent it. Automation doesn't fail because the technology breaks. It fails because organizations can't accept it. The predictable disaster. A telecommunications company built automation that worked brilliantly. It could update network equipment in minutes instead of hours. Errors dropped to nearly zero. Leadership was thrilled. They approved the budget and rolled it out. 18 months later, that same automation was collecting dust. Engineers were working around it. The change management team was blocking it. Security wanted it shut down entirely. The company went back to doing everything manually, except now they had wasted money and lost faith in automation altogether. This isn't a one-off horror story. This is the normal outcome when organizations try to automate their networks. Here's the surprising part. The automation still worked perfectly. The technology was fine. What failed was everything around it. The organization simply couldn't accept it. This chapter explains why organizations reject working automation and what you need to build instead. The 4 ways organizations kill good automation. Think of automation like a new employee trying to succeed in your company. To be successful, they need to pass through 4 distinct levels. Most automation fails at level 2 or 3, not level 1. Level 1. Does the job work? Almost never the problem. This is where everyone focuses their energy. Can the automation actually configure the router? Can it update the firewall? If you're a skilled engineer, the answer is almost always yes. You can prove it works on your laptop. You can show a demo to your boss. Technically, it's a success. But in a large company, working is only the beginning. Level 2. Who owns it? The first point of failure. This is where the trouble starts. You built the automation, but you have a day job. 6 months later, you're promoted or you move to a different team. Who looks after the code now? Who fixes it when the network vendor releases a software update that breaks your script? If there isn't a formally designated owner with a budget and allocated time, the automation becomes a waif. People start to fear using it because they don't know who to call when it breaks. Eventually, they stop using it altogether. Level 3. Is it safe? The security veto. One day, the security team hears about your automation. They ask, where are the passwords stored? You tell them they're encrypted in a local file. They ask, who has access to trigger this? You say, anyone with the script. The security team immediately sees a massive risk. They see a tool that can change the entire network in seconds with almost no oversight. They don't care how much time it saves. They care that it's a black box they can't control. They exercise their veto and the project is shut down. Building for acceptance, not just execution. To succeed, your automation architecture must address all 4 levels from day 1. You aren't just writing code, you're building an organizational capability. This means your architecture must address ownership, governance, integration with change management so every action is authorized, security, centralized vaulted access that the security team trusts, and safe failure. Environment where you can test changes safely before they touch the real world. Quick health check. Ask yourself these questions honestly. Ownership. Is there a formally designated owner? Do they have allocated time and budget? Would it survive if they left tomorrow? Governance. Does it integrate with your change management system? Can you prove who requested, approved, and executed each change? Do you have tested rollback procedures? Security. Are passwords and access keys stored securely, not in the code? Has your security team approved the design? Does it have only the minimum access it needs? Safe failure. Are development, test, and production environments separated? Do you test on a small group before deploying to everything? Can the automation detect its own errors and stop automatically? If you answered no to any of these, you've identified why your automation might fail organizationally. A no in security or safe failure represents potential catastrophic risk, regardless of everything else. Takeaway: technical success is necessary. Organizational acceptance is what makes automation succeed. You need both. The next chapter explains how to build automation that organizations will actually trust and use long-term.
It is a lot to think about, is it not? Technical success is only the first step. If we want our automation to actually survive in the real world, we have to build for ownership, security, and audit from the very beginning. If you found this helpful, please subscribe to my channel and leave a comment below with your thoughts. I would love to hear which of these 4 levels is the biggest challenge in your organization right now. In the next chapter, we are going to look at why a tool that saves you time might not be ready to save the company time. I will see you there. Welcome back. This is Brandon here again. We are moving on to chapter 2. I am handing things over to Archird to walk us through a very important lesson. We often build tools that save us a lot of time personally, but we quickly discover that what works for one person does not always work for the whole company. We are going to look at why moving from personal productivity to organizational capability requires a completely different approach. Let us join Archird for Chapter 2.
Chapter 2. Why your brilliant time saver won't work for the whole company. Yet. What saves you time and what saves the company time are 2 completely different things. The question that changes everything. You've built something that works beautifully. A task that used to take 4 hours now takes 10 minutes. Your manager is impressed. Other teams hear about it. Word spreads. Then someone in leadership asks, can we roll this out across the entire organization? The honest answer is, not yet. We'd need to rebuild it first. The answer people actually give is, sure, we just need to write some documentation and share the code. This is where most automation dies. Not immediately, slowly, over about 18 months as the organization discovers that what worked perfectly for you doesn't work at all for everyone else. Here's what most people don't understand. Automation that makes you more efficient and automation that makes your organization more capable are fundamentally different things. They're not the same system at different sizes. They're different architectures altogether. This chapter explains what changes when you move from personal productivity to organizational capability, and why getting this wrong costs so much money. The 3 levels and why only one actually scales. Think of automation maturity as 3 distinct levels. Most people assume they're just upgrades of each other, like iPhone models. They're not. They're as different as a bicycle, a car, and a bus. Level 1, just for you. This is where everyone starts. You've written something that helps you do your job faster, you run it when you need it, you fix it when it breaks, you understand how it works because you built it. Who owns it? You, obviously. Who approves changes? Nobody. It's your tool. What happens if you leave? It stops working. How long does it last? Weeks to months. This is perfectly fine for personal productivity. The problem starts when organizations try to use level 1 automation as if it were level 3. Think of it like your personal spreadsheet for tracking expenses. Works great for you, but it is useless for running the finance department. Level 2, shared by your team. The danger zone. This is where things get dangerous. Your script is now being used by your whole team. Other people run it, but you still fix it when it breaks. There's maybe a README file. Knowledge is shared through personal relationships. Who owns it? Still you, informally. Who approves changes? Peer review when people remember. What happens if you leave? Slowly breaks, eventually abandoned. How long does it last? Months to a year. Here's why level 2 is the most dangerous. It looks like organizational automation, but it doesn't have any of the structure that makes organizational automation safe. It has the reach of level 3 automation with the governance of level 1. Think of it like running a restaurant using recipes scribbled in one chef's personal notebook. It works great until that chef leaves, then chaos. When level 2 automation breaks, it doesn't just affect you anymore, it affects your entire team. Most automation gets stuck here, causes an incident, and the organization shuts it all down. Level 3, enterprise automation, what actually works long-term. This is automation the organization depends on. Multiple people can maintain it, someone formally owns it with allocated time. It integrates with your change management system. There's comprehensive documentation. Audit trails satisfy compliance requirements. Who owns it? Formally designated owner with backup. Who approves changes? Your organization's change management process. What happens if the owner leaves? Backup owner takes over, system continues. How long does it last? 5 years or more. This is what people think they're getting when they ask, can we roll this out? This is what actually works long-term. Think of it like the difference between one person's filing system and your organization's official records management system. One is personal convenience, the other is organizational infrastructure. What actually changes between levels? Let's be specific about the differences. Who owns it? Personal tool? You. Everyone assumes. Enterprise capability? Named person with backup, officially designated. Who approves changes? Nobody. You just do it. Enterprise capability? Change management process. If the owner quits, personal tool, it dies. Enterprise capability, backup continues. How long does it last? Personal tool, weeks to months. Enterprise capability, 5 years minimum. Documentation, personal tool, maybe some comments. Enterprise capability, full guides, architecture, operations, troubleshooting. Who can fix it? Just you. Enterprise capability, at least 3 people. The question isn't whether your automation works, the question is whether it can survive as an organizational capability. The 4 things enterprise automation actually needs. If you want automation that your organization will trust and depend on long-term, you need these 4 foundations. Miss any one and you're building something that will eventually fail organizationally. Foundation 1, real ownership. Someone is formally designated as the owner with 20 to 40% of their time officially allocated to this. There's a backup owner with 10 to 20% of their time allocated. Maintenance is part of their job description and performance reviews. Ownership without allocated time isn't ownership. It's asking someone to maintain automation in their spare time whilst doing their regular job. Critical infrastructure needs dedicated resources. Foundation 2, proper governance. Execution requires approval. Someone requests a change, someone else approves it, and the automation executes it. Changes go through your organization's standard change management process, and every action creates an audit trail showing who did what. Governance isn't bureaucracy. It's how organizations demonstrate accountability to auditors and limit damage when things go wrong. Bigger impact requires oversight. Foundation 3, visibility. You need centralized logging that monitoring systems can read, real-time dashboards and alerts when something goes wrong. If your automation breaks and nobody notices for 3 hours, that's not automation you can trust with business-critical tasks. You need to know about problems before they become disasters. Foundation 4, sustainability. You need documentation that someone who wasn't involved in building this can actually understand. You need at least 3 people who can maintain it, the bus factor. If only you understand how it works, you haven't built organizational capability. You've built organizational dependency on you personally. Organizations need recipes, not secrets. How organizations learn to trust automation. Trust isn't binary. Organizations move through levels and each requires proof. Level 1 trust, tell me what you do. The automation runs in read-only mode and reports what it would change. Risk is minimal. Level 2 trust, prepare changes for my review. The automation generates changes, but a human reviews and applies them manually. Risk is low. Level 3 trust, execute after I approve. The automation makes changes automatically, but only after a human approves each action. Risk is moderate. Most enterprise automation should stop at level 3. Fully autonomous automation exists, but most organizations don't need that level of maturity. 3 hard lessons from real failures. The one-person show. A firm had critical automation maintained by 1 senior engineer. When he resigned, 3 people spent 6 weeks trying to understand it. They eventually rewrote it from scratch because retro-engineering it was harder. The compliance disaster. A government department ran network automation for 18 months before an audit discovered it had no change management integration or individual accountability. It was flagged as a potential insider threat and immediately shut down. The knowledge vacuum. A provider had excellent automation built by one developer. When she left, the automation broke within 3 months, and her replacement needed 6 months to understand the codebase. What you need to believe. What saves you time and what saves the company time are two different problems requiring different designs. Level 2 is where automation goes to die. Either keep it at level 1 or invest in moving it to level 3. The 4 foundations aren't optional: ownership, governance, visibility, sustainability. Miss any one and you're building something that will eventually fail organizationally. Ownership requires allocated resources. Assigning someone as owner without reducing their other work is setting them up to fail. It's like making someone responsible for fire safety in their spare time. Trust is earned through demonstration. Organizations trust what they can verify, monitor, and hold accountable. Build those capabilities or accept limited trust. The bus factor measures sustainability. If your automation can't survive losing 1 or 2 key people, it's a single point of failure pretending to be organizational capability. The transition costs real money, between $50,000 and $150,000 and 6 to 12 months. Organizations unwilling to invest this should keep automation at level 1 with appropriate safeguards. Knowledge concentration breaks automation politically. If only 1 or 2 people understand it, the organization has created dependency, not capability. People resist depending on systems they don't understand. Structure enables, it doesn't restrict. The 4 foundations aren't bureaucracy. They're the architecture that allows organizations to trust automation enough to depend on it. The next chapter examines how to actually build this structure, the systems, processes, and integration points that make enterprise automation work in practice.
It's a lot to take in, is it not? Moving from a personal tool to an organizational capability is the only way to make automation last. The 4 foundations of ownership, governance, visibility, and sustainability are not just red tape. They are the architecture that allows the company to trust your work enough to actually depend on it. If you found this helpful, please subscribe to my channel and leave a comment below. I would love to hear which of these levels your team is currently working in. In the next chapter, we are going to look at systems and processes that make enterprise automation work in practice. I will see you there. Hi, this is Brandon. Chapter 3. Enterprise automation is a structural challenge, not just a programming one. You can have the best code in the world, but without a steering wheel and brakes, you are just building a faster disaster. Archird is going to share a story about a utility provider that learned this the hard way. Let's listen and learn.
Chapter 3. Why automation needs structure, not just better code. Automation doesn't remove the need for control. It makes control enforceable in ways manual work never could. When helpful scripts become dangerous systems. Every automation project reaches the same turning point. What started as a few helpful scripts becomes something much bigger. A system capable of making thousands of changes across critical infrastructure with minimal human oversight. This is where most organizations fail, not because their tools are inadequate, but because they never treated automation as a structural problem requiring intentional design. The failures are predictable. An outage at 3 a.m. because a script assumed something would always be there. An audit failure because nobody can prove what version of the automation ran 3 months ago. A regional office offline for 6 hours because the only person who understands the system is on leave. These aren't tool failures, they're structural failures. This chapter establishes a foundational principle. Automation in enterprise environments must be designed, governed, and operated with the same discipline as the infrastructure it manages. Anything less scales risk faster than capability. Why scripts can't scale, even good ones. The difference between a script and a system isn't size or complexity, it's intent and life cycle. A script solves an immediate problem for one person in a controlled context. It lives in someone's personal folder. It depends on that person's specific knowledge to run. If it fails, the person who ran it fixes it. The system is the human being using the script as a tool. A system is designed to outlive its creator. It has defined inputs, predictable outputs, and built-in safety mechanisms. It doesn't live on a laptop, it lives in a governed environment. It is operated by people who didn't write it, following processes they didn't invent. When you try to run an enterprise network using a collection of scripts, you're essentially building a high-speed train, but using a person with a handheld lantern to check the tracks. It works as long as the person is awake, the lantern is lit, and the train isn't moving too fast. But eventually, the scale of the automation exceeds the human's ability to provide the structure for it. The electricity provider incident. I once investigated a major incident at a large electricity provider. Their network team had written a clever set of instructions to manage security updates. It was a brilliant time saver that ran perfectly for months. One Saturday at 3 a.m., the script started a routine update. However, it encountered a situation the author had not expected. A single network switch was slightly different from the others. Instead of stopping and asking for help, the script did what it was programmed to do. It kept trying to force the change. Because there was no safety cage around the script, it created a digital feedback loop. By 3:30 a.m., the entire corporate network was dark. Technicians in the field could not see the maps required to fix power lines, and customer service could not take emergency calls. It took 12 hours to manually untangle the mess. The problem was not bad code. The problem was that the company had a powerful engine, but no steering wheel, no brakes, and no dashboard. What structure actually looks like? In a professional automation architecture, we separate three things that scripts usually mix together. The source of truth, the intent. This is where we define what the network should look like. It's not a script, it's a database or a file, like Git, that holds the gold standard configuration. The control layer, the brain. This is the part that decides when and how a change happens. It checks if the change is approved, validates that the instructions are safe, and ensures the person triggering the change has the right authority. The execution engine, the muscle. This is the part that actually talks to the routers and switches. It doesn't think, it just does what the control layer tells it to do. By separating these, we create a system where we can change our muscle, moving from one tool to another without losing our brain, our safety rules and approval processes. The cost of no structure. Building without structure feels faster on day one, but the interest rates are astronomical. The hero dependency. Without structure, you depend on Bob to run the script. If Bob is on holiday, the work stops. The audit nightmare. When an auditor asks who approved the change 6 months ago and your only record is a text file on a decommissioned laptop, the automation program will be shut down. The inevitable rebuild. Eventually, the lack of structure will cause an incident so large that the organization will lose faith. You'll be forced to rebuild everything under extreme pressure and scrutiny. What you need to believe. Automation at enterprise scale is a structural problem, not a tooling problem. Better tools won't save you if your structure is wrong. Separating control from execution is foundational. It enables everything else: audit, safety, longevity, and trust. It is not optional. Scripts work until the organization depends on them. At that point, lack of structure becomes the constraint on reliability, not the capabilities of your tools. Changing tools won't fix structural problems. Switching platforms doesn't matter if the architecture is wrong. Structure matters more than tools. Trust comes from demonstrated failure containment, not from demonstration of successful changes. It is built through reproducible evidence of compliance and operational longevity through staff changes. Building structure requires effort that feels premature. When you only have 3 scripts, the investment seems excessive. The return appears when you have 300 scripts across 5 teams and they still work reliably because the foundation was sound. Treat automation as infrastructure from day one, or accept that you'll rebuild it under pressure later. There is no middle path that scales. Knowledge concentration is organizational fragility. If only 1 or 2 people understand it, you haven't built capability, you've created dependency. The next chapter examines the specific systems and processes that make this structure real in production environments.
And that is why the blueprint is more important than the hammer. We have moved from the why of enterprise scale to the how of structural integrity. By separating the brain from the hands, we make sure our automation is a tool for progress, not a source of accidental chaos. I would love to hear from you. Have you ever seen a weekend project grow into a corporate headache? Leave a comment below and let us talk about it. And if this structural approach makes sense for your network, be sure to subscribe so you do not miss the next one. Coming up in Chapter 4, we are taking these principles and applying them to your actual infrastructure to build a truly resilient system. Thanks for listening, and I will see you in the next chapter. Welcome back. This is Brendan here again. Let's continue our reading with Chapter 4. Listen, follow the slides, and enjoy the content as we look at how to build an architecture that makes a total network blackout practically impossible. We're talking about real safety today, specifically how to build a system that protects your team from the inevitable human error. Let's jump in.
Chapter 4. Building a safe automation system for your network. The best safety system is one that makes dangerous mistakes difficult to make in the first place. When automation goes wrong. At 3:47 a.m. on a Tuesday morning, a financial services company pushed a routine network update to their data centers. Within 8 minutes, 2,400 automated trading systems went offline. The company lost the ability to process transactions for 6 hours. The incident cost approximately $18 million in lost revenue and regulatory fines. The problem wasn't the change itself. The configuration update was correct and had been tested. The problem was that a junior engineer, working late and fatigued, ran the automation script against the production network instead of the test network. There was nothing in the system to stop this from happening. The engineer simply typed the wrong command, pressed enter, and within minutes, trading floors across Europe couldn't access the network. This chapter explains how to build an automation system that prevents these disasters, not through better training or stricter procedures, but through architecture that makes dangerous mistakes physically difficult to make in the first place. What we're building and why. Think of network automation like the systems that control a modern airport. Planes take off and land safely thousands of times per day, not because pilots never make mistakes, but because the system has multiple layers of protection. Air traffic controllers verify clearances. Automated collision avoidance systems monitor the sky. Standardized flight plans are validated before the engines even start. In network automation, we need the same thing. We need an environment where a single typo at 3 a.m. cannot destroy the business. The 5 requirements that cannot be compromised. To build a safe, professional system, your architecture must satisfy 5 specific requirements. These are not nice-to-have features. They are the foundation of enterprise-grade automation. 1. Making dangerous actions difficult. The system must have physical constraints that prevent people from accidentally doing the wrong thing. For example, a car shouldn't allow you to engage the starter motor whilst the engine is already running. In our world, this means the automation tool should be technically incapable of connecting to the production network unless it has passed through specific safety checks. The source of truth, blueprints versus digging holes. When you want to know how the network is currently configured, where do you look? Most engineers dig a hole. They log into the router and look at the settings. This is dangerous. If the router is already misconfigured, your automation will build on top of those errors. A safe system uses a source of truth, usually a Git repository. This is the master blueprint of what the network should look like. The automation always compares the real network to the blueprint. If they don't match, it fixes the network to match the blueprint. You never dig holes. You always trust the blueprints. Separation of intent and execution. The brain, the logic that decides what to change, must be separate from the muscle, the tool that actually pushes the buttons. This allows you to test your logic in a safe environment before you ever allow it to touch a real device. The safety gates. Before any change is applied to the network, it must pass through an automated assembly line with 3 specific gates. The inspector, software that reads your instructions and checks for obvious errors like a typo in an IP address. The mirror, a test environment that looks exactly like your production network, where the change is applied first to see if it causes a problem. The witness, a system that records exactly who proposed the change, who approved it, and what the results were. Visibility and audit. In a professional system, you never ask, "I wonder what changed yesterday." The system tells you. Every action is logged in a way that satisfies auditors and allows you to recover quickly if something goes wrong. Takeaway: don't train your people to be perfect. Build a system that protects them when they aren't. Why this matters for your career. Building this way is harder than just writing a script. It takes more time and requires more planning. But it's what separates a scripter from an architect. An architect doesn't just provide a tool that works, they provide a system that the business can trust with its most valuable assets. The architecture provides the safety net that allows moving faster with confidence. The architecture scales because it automates governance. At 50 devices, manual approvals and script execution work acceptably. At 5,000 devices, manual processes become bottlenecks and error sources. This architecture removes those bottlenecks by treating governance as automated enforcement, not as human process. Every compromise on these principles creates technical debt that compounds. The most expensive problems I've investigated started with someone saying, "We'll do it properly later, but right now we need to move fast." Years later never came, and the shortcuts became foundational assumptions that were expensive and risky to fix. If you implement one thing, treat your master record, Git, as the definitive source of truth from day one. Every shortcut around this principle, quick manual fixes, configurations stored in spreadsheets, temporary changes that never get documented, create a gap between what your automation thinks the network looks like and what it actually looks like. That gap is where disasters hide. The goal isn't perfection, it's recoverability. You cannot prevent all failures, but you can build a system where failures are detected quickly, contained to small areas, and recovered automatically. The difference between an incident that takes 5 minutes to fix versus 5 hours to fix is usually whether your automation architecture was designed for recovery from the beginning.
And that's a wrap on Chapter 4. The big takeaway here is that a truly safe system isn't built on human perfection. It's built on those architectural fire doors and master blueprints that catch us when we trip up. By removing that messy direct access and locking in a single source of truth, we've finally created an environment where moving fast doesn't have to mean taking big risks. I'd love to know, how are you handling your fire doors right now? Drop a comment below and let's chat about it. If you found this helpful, please subscribe to my channel and leave a comment below with your thoughts or questions. I'd love to hear how you're applying these structures in your own network. In our next session, Chapter 5, Testing Changes Safely Before They Go Live, we'll look at the actual mechanics of the testing gate and how to verify your code before it ever sees a production switch. See you in the next one. Hey there, Brendan. Back with you for Chapter 5. Archird is standing by to walk us through the real world of testing. We are moving away from those perfect, clean labs and looking at how to handle the messy reality of your actual production network. Grab your coffee, follow along with the slides, and let us learn how to build a proper safety buffer so your automation never turns into an expensive surprise. Let us get into it.
Chapter 5. Testing changes safely before they go live. If you can't break it safely in testing, you'll break it dangerously in production. When testing means nothing. At 2:15 p.m. on a Wednesday, a telecommunications company deployed new network automation to update security settings across their infrastructure. The automation had been tested in their laboratory. It worked perfectly on the 10 devices in the lab. The engineer confidently deployed it to production. Within 20 minutes, 847 branch offices lost internet connectivity. Customer service centers couldn't process orders. Retail locations couldn't accept credit card payments. The company lost approximately $3 million in revenue during the 8-hour recovery period. Regulatory fines added another $500,000. The problem wasn't that the automation failed. The automation worked exactly as programmed. The problem was that the laboratory contained 10 identical devices running current software, whilst production contained 847 devices of 12 different models running 7 different software versions. The automation worked on current software. It catastrophically failed on older software versions that the laboratory never tested. This chapter explains how to build a safety system that actually protects your production network, not one that merely gives you false confidence before disasters occur. Why most testing fails to protect you. Walk into most organizations and ask about their testing approach. They'll show you a shelf of spare equipment in the corner of the data center. They call this the lab. They might even have a small virtual environment running on a server. The problem with these labs is that they are perfect worlds. They are clean, simple, and consistent. Your production network is none of those things. Production is a messy world of legacy equipment, weird configurations made during 3 a.m. emergencies, and software versions that should have been upgraded 5 years ago. Testing in a perfect lab proves only that your automation works in a perfect lab. It tells you nothing about whether it will survive the reality of your production network. The 3 environments. Building the safety buffer. To protect your business, your architecture must separate the journey of a change into 3 distinct rooms or environments. 1. The sandbox, where you experiment. This is a purely virtual environment where engineers can try new ideas without any risk. It doesn't need to look like the real network. It's like a sketch pad for an architect. If you break the sandbox, nobody cares. You just delete it and start again. 2. The staging area, the digital twin. This is the most important part of your architecture. The staging area must be a digital twin of your real network. It must have the same equipment models, the same software versions, and the same complex configurations as production. If production has a 10-year-old switch running buggy software, your staging area must have that same 10-year-old switch. Your automation must prove it can handle the messy reality here before it is allowed anywhere near your customer's data. The 3rd environment is production, the no-go zone. This is the live business network. In a professional architecture, no human ever makes a change directly in production. Instead, you promote the code. Once the automation has been proven in the staging area, the exact same code is moved into production by the system, not by a person. The golden rule of testing: identical code. The biggest mistake teams make is having different versions of their automation for different environments. They have a test script and a production script. This is a recipe for disaster. If you change the code between testing and production, you haven't actually tested the code you are running. A safe architecture ensures that the exact same instructions are used in every environment. The only thing that changes is the target, the network the instructions are pointed at. Takeaway: a lab is for learning. A staging area is for proving. You need both to survive. The strategy of safe promotion. How do you move code safely from the sandbox to production? We use a process called a pipeline. Think of a pipeline like an automated assembly line in a car factory. At each stage, the car is inspected. If a bolt is loose, the assembly line stops immediately. The car is not allowed to move to the next station until it is perfect. Your network automation should work the same way. Stage 1, the code is written in the sandbox. Stage 2, an automated linter checks for typos and security risks. Stage 3, the code is deployed to the staging area. Stage 4, automated tests verify that the network is still working correctly. Stage 5, Only after all previous stages pass is the code promoted to production. What you need to believe. If you can't break it safely in testing, you'll break it dangerously in production. Testing in an environment that doesn't mirror production is merely theater. It provides false confidence that masks real risk. The staging environment is your most valuable security control. It is the only place where you can prove that automation handles the messy reality of legacy equipment and varied software versions. Code must be immutable across environments. Never use separate code for different environments. Code duplication guarantees eventual inconsistency and multiplies maintenance work. Test for failure, not just success. If automation cannot fail safely and roll back reliably, it cannot be trusted to succeed in production. Deliberate failure testing exposes problems before production encounters them unexpectedly. Enforce separation of responsibilities technically, not just procedurally. Policy documents that can be bypassed don't satisfy regulatory requirements or provide real protection. Technical controls that prevent bypass do both. If you implement one thing from this chapter, make code promotion automatic and ensure the code is identical across all environments. This single decision prevents the majority of testing-related failures. When tests succeed with code version 2.4.1, production deploys exactly that same version 2.4.1. Not a similar version, not a manually updated version, but the identical tested code. This gives you genuine confidence that production will behave like testing predicted. The effort invested in proper environment separation and testing seems excessive when you're building your first few automation scripts. The value becomes obvious when you have dozens of automation jobs, multiple engineers working simultaneously, and auditors requesting evidence of your last 100 changes. By then, retrofitting proper separation is expensive and disruptive. Building it correctly from the start is cheaper in the long run.
And that is why the staging area is your absolute best insurance policy. True reliability comes from testing against the messy reality of your network. Not just a perfect lab. If you have ever had a change work in the lab but fail in production, tell me about it in the comments. I would love to hear what happened. Up next in Chapter 6, we are talking security, specifically how to manage the keys to the kingdom. I will see you there. Hello again. I am Brendan, and we are moving into Chapter 6. This is a big one. We are talking about the keys to the kingdom. Archird is going to explain why shared passwords are a disaster waiting to happen, and how to build a system that even your security team will love. It is all about moving from trusting people to trusting the system. Let us join Archird for Chapter 6.
Chapter 6: Keeping Passwords and Access Safe. A password that everyone knows is a disaster waiting to happen. When one password becomes everyone's problem. At 11:47 p.m. on a Friday, a financial services company discovered that someone had modified firewall rules across their network, opening access to sensitive customer data systems. The changes were made using the automation account, a shared password that their network automation systems use to make configuration changes. The security team needed to answer 3 urgent questions. Who made these changes? Were they authorized? Was this an attack or a mistake? They couldn't answer any of them. The log showed only that the automation account had logged in and made changes. They had no way to determine which automation job had run, which person had triggered it, or whether it had proper approval. The shared password had been used by automation systems for 2 years. 15 engineers had accessed it at various points. 3 of those engineers no longer worked at the company. The incident investigation took 6 weeks. The company ultimately paid $2.3 million in regulatory fines for inadequate access controls and incomplete audit trails. They could never definitively determine whether the changes were malicious or accidental. This chapter explains how to manage passwords and access for automation systems so you always know exactly who did what, when, and under whose authority. Why shared passwords are dangerous. Most organizations start their automation journey by creating a single service account with a powerful password. They give this password to every engineer who needs to run a script. In a professional architecture, this is unacceptable for 3 reasons. Zero accountability. If everyone uses the same key, you can never prove who opened the door. The leaving engineer problem. When an engineer leaves the company, you have to change the password on every single piece of equipment. Because this is hard and risky, most companies just don't do it, leaving a massive security hole. No limit to the damage. A shared automation password usually has God mode access. If that password is stolen, the attacker can destroy the entire network in seconds. The solution: the secret vault and unique identities. A safe automation architecture never stores passwords in a text file or script. Instead, it uses a secret vault, like HashiCorp Vault, Azure Key Vault, or CyberArk. Here is how a professional system handles access. The vault. All passwords are stored in a central, encrypted digital safe. The automation ID. Every specific automation task has its own unique identity. It doesn't use a human password. Just-in-time access. When the automation needs to make a change, it asks the vault for a password. The vault gives it a temporary password that only works for that specific task and expires as soon as the job is finished. The digital signature. Because the vault knows exactly which job requested the password, it creates an audit trail. Now we know that job number 452, triggered by Sarah, approved by Mike, used this password at 2 p.m. Takeaway: stop managing passwords, start managing identities. What you need to believe. If you implement one thing from this chapter, stop using shared passwords and implement unique identities per automation function, managed through a dedicated password vault. This single change addresses the majority of password-related security problems and satisfies most regulatory requirements for access control. Hard rules to take forward. Never store passwords in code or local files. Credentials must be fetched from a secure vault at runtime. Hard-coded secrets are a primary target for attackers and an automatic audit failure. Unique identities are mandatory. Automation must use unique service accounts that are distinct from human accounts. Shared accounts create unidentifiable risk and complicate revocation. Enforce separation of duties through technical controls, not policies. Multiple people must be involved in critical changes, enforced by systems that make single-person control impossible, not just forbidden. Audit trails must be complete and immediately searchable. Minimal logging that requires manual investigation is inadequate. Each event must include complete context, enabling full understanding without correlating across multiple systems. Limit permissions to minimum required for specific functions. Each password should have precisely the access needed for its specific automation job, and nothing more. Calculate and document acceptable risk if passwords are compromised. The investment in proper password and access management seems excessive when building your first automation. The value becomes obvious when facing your first security incident, your first audit, or your first investigation trying to determine what happened 6 months ago. By then, retrofitting proper controls is expensive and disruptive. Building them correctly from the start is cheaper in the long run and prevents disasters that proper controls would have avoided entirely.
Security is not something you bolt on at the end. It is a fundamental part of the architecture. If your security team is currently blocking your automation projects, it is probably because they do not see this kind of structure. When you can prove exactly who did what, and show that passwords are never shared, you turn the security team from a roadblock into a partner. In the next chapter, we are going to look at using programming to catch mistakes before they ever reach the network. I will see you there. Brendan here. Welcome to Chapter 7. This is where we take the power of programming and turn it into our biggest safety net. We are not just writing code to make changes. We are writing code to stop bad changes. Archird is going to explain why a single digit can cost millions of dollars, and how we can use automated validation to make sure that never happens to you. Let us get into it.
Chapter 7. Using programming to catch mistakes before they ever happen. The best code you'll ever write is code that stops bad changes before they reach production. When automation runs without checking first. At 3:15 a.m. on a Saturday, a telecommunications company's automation system began deploying a routine network update across their infrastructure. The update had been tested in the laboratory. The deployment instructions were clear. Everything looked ready. Within 12 minutes, 420 network devices across Australia and New Zealand stopped working correctly. Internet service failed for approximately 380,000 customers. Mobile phone connectivity dropped for an additional 150,000 subscribers. The automated recovery systems couldn't function because they relied on the same broken network infrastructure. The problem wasn't a software bug or a hardware failure. The problem was a simple data entry error. Someone had typed 255.255.255.0 where they should have typed 255.255.254.0. A single digit wrong in a configuration file. The automation system never checked whether this number made sense. It simply applied the wrong setting everywhere, exactly as instructed. Recovery required 18 hours of emergency work by engineers manually visiting sites and correcting configurations device by device. Direct costs exceeded $5.5 million. Regulatory fines added another $2.4 million. The incident was entirely preventable with proper validation before deployment. This chapter explains how to use programming, specifically Python and structured data, to catch these mistakes before they ever reach your network equipment. The difference between doing and validating. Most beginners use programming to do things. Log in to the router, type this command, save the config. In a professional architecture, we use programming to validate things. Is this IP address valid? Does this change overlap with an existing service? Does the person requesting this have the authority to change this specific site? The 3 gates of validation. A safe system uses 3 different types of checks before it allows a single line of configuration to be sent to a router. Syntactic validation, the typo check. This is the simplest level. The code checks that the data is in the right format. Is an IP address actually 4 numbers? Is a VLAN ID between 1 and 4094? This catches the $7.9 million we discussed earlier. Semantic validation, the logic check. This is deeper. The code checks if the change makes sense in context. You might be trying to assign an IP address that is already in use elsewhere, or trying to delete a connection that a critical customer depends on. The code reads the whole network map and says, wait, if you do this, you'll break that. Policy validation, the permission check. This checks if the change follows the company rules. For example, no changes to the core network are allowed during business hours, or all firewall changes must be approved by the security manager. Why this makes you faster? It sounds like validation would slow you down. In reality, it makes you much faster. When you know the system will catch your mistakes, you can move with confidence. You stop spending hours triple-checking every line of code because you've built an automated assistant that does it for you, perfectly, every single time. Takeaway: don't just automate the work, automate the wisdom required to do the work safely. What you need to believe. If you implement one thing from this chapter, build validation that runs before deployment and rejects changes that don't meet requirements with clear, specific error messages. This single improvement prevents the majority of automation-caused incidents. Hard rules to take forward. Automation must be self-aware. It must understand the rules of the network it is changing. If a change violates a rule, the automation must refuse to execute and alert a human. Separation of data and logic. Store your network details, IPs, VLANs, site names, in a structured format like YAML or JSON, and keep your Python code separate. This makes it easier to audit and harder to break. Fail loudly and early. If validation fails, the system should stop immediately and provide a clear explanation of why. Never allow the system to guess or try to fix a mistake automatically. Validation is not optional. Every change, no matter how small, must pass through the same validation pipeline. Emergency changes are when mistakes are most likely to happen, so they need validation more than anything else. The effort invested in proper validation seems like overhead when building your first automation. The value becomes obvious the first time validation catches a problem that would have caused a production outage, or when auditors ask for compliance proof and you provide code and test results instead of policy documents. Building validation properly from the start is far cheaper than dealing with the incidents that improper validation allows through.
Validation is the secret weapon of the professional architect. It is what allows us to sleep at night, knowing that a simple typo cannot take down the entire company. If you have ever been saved by a validation check, or if you wish you had one, let me know in the comments. I would love to hear about it. In the next chapter, we are going to look at the execution engines, the muscle that actually makes the changes happen once they have passed all of our safety gates. I will see you there. Here, we are moving on to Chapter 8. This is where we talk about the muscle of our system. We often get caught up in debates about which tool is better, but as Archird is about to explain, the tool matters much less than the architecture it sits within. We are going to look at how to stop the cycle of swapping tools and start building a system that lasts. Let us join Archird.
Chapter 8: Execution Engines in Context. The tool is the hammer. The architecture is the blueprint. A hammer cannot build a house without a plan, and an automation tool cannot secure a network without a proper system around it. The tool swapping trap. I've watched the same expensive mistake play out at banks, government agencies, and utility companies. It goes like this. A team announces they're building an Ansible system or becoming a Terraform shop. 6 months later, they're replacing Ansible with Python. A year after that, they're testing a vendor's product. 2 years in, they've spent hundreds of thousands of dollars, and their network automation is no more reliable than when they started. The problem isn't the tools. The problem is they never built a proper system. Think of it this way. Ansible, Terraform, and similar products are like power drills and saws. They're useful, but they don't build houses by themselves. You need architectural drawings, building inspections, electrical codes, and project managers. Without those, you're just buying increasingly expensive tools whilst the house remains unbuilt. This chapter explains how automation tools fit into a complete system and why picking the right tool is never your main problem. What execution tools actually do. Execution tools are the only components allowed to actually touch your network equipment. This isn't just good practice, it's a security wall. In a properly designed system, no engineer can log into a router directly. Instead, they submit their intent to the control layer. The control layer validates the request, checks the approvals, and then, and only then, does it tell the execution engine to do the work. The execution engine's job is simple but critical. Translate. Turn high-level instructions into specific language the router understands. Connect. Securely log into the equipment. Verify. Make sure the change actually happened and report back to the control layer. Why the best tool doesn't exist. I often get asked, which is better, Ansible or Terraform? The answer is always, it depends on the job. Trying to pick one tool for everything is like trying to build a whole house using only a screwdriver. You could probably do it, but it would be a terrible house and take far too long. A professional architecture is tool agnostic.
This means that the brain of your system, the control layer, is designed so that it can talk to any tool. If you want to use Ansible for your legacy switches and Terraform for your cloud firewalls, your architecture should support that without you having to rewrite everything. The muscles versus the brain. The biggest mistake organizations make is letting the tool define the process. If you build an Ansible process, you are stuck with how Ansible thinks. If you move to a new tool in 3 years, you have to throw everything away and start again. When you build a proper system, the brain stays the same even if you swap out the muscles. You keep your security rules, your approval processes, and your history, even if you swap out the tools that talk to the routers. Takeaway: build the system first. Pick the tools second. Hard rules to take forward. Tools don't define your system. If swapping a tool requires redesigning your governance model, you never had a system in the first place. Separate building from configuring. Infrastructure tools create resources. Configuration tools manage device settings. Don't mix these jobs. Centralize execution. All tools must be triggered by your pipeline system, never manually from someone's laptop. Safe rerunning is mandatory. If a tool can't safely run against already configured equipment, it doesn't belong in production. Define the connections between layers. The contract between layers matters more than any specific tool's implementation. If you finish this chapter still believing your main challenge is Ansible versus Terraform, you've missed the point. Your main challenge is designing an execution layer that will outlive any specific tool.
It is easy to get distracted by the latest shiny tool, but a professional architect focuses on the system. When you build an architecture that is tool agnostic, you are protecting the company's investment and making sure your work will still be valuable years from now. If you have ever been caught in a tool war at work, let me know in the comments soon. I would love to hear how you handled it. In the next chapter, we are going to look at the heart of organizational trust, change management, and audit. I will see you there. We are moving in Chapter 9. This is where we talk about governance. Most people think of change management as a slow process that gets in the way of work. But, as Archird is about to explain, proper governance is actually what makes speed safe. We are going to look at how to build audit trails and approvals directly into your code, so that your automation is always compliant and ready for any investigation. Let us join Archird.
Chapter 9: Change Management and Audit. Governance is not an obstacle to speed. It is the framework that makes speed safe. If a change cannot be traced, it did not happen. It was an incident. The speed without control problem. I reviewed automation systems that can set up 1,000 network segments in under 5 minutes. Technically impressive, practically useless. Why? Because when the auditor asked, "Who approved this change?" the answer was, "It came from our code repository." When the regulator asked, "How do you prevent unauthorized modifications?" the answer was, "We trust our engineers." When the post-incident review demanded what exactly changed at 2:37 in the afternoon, the answer was, "We'll have to check the equipment logs." These systems failed not because they were slow, but because they had no controls. Speed without governance isn't automation, it's amplified risk. This chapter addresses the hardest problem in automation: combining the speed of code-driven change with the rigor of organizational oversight. If you finish this chapter still believing that change management is something you add later, or that audit trails are nice to have, you'll build systems that collapse the first time a regulator, an executive, or a major incident demands accountability. The invisible risk problem. When automation exists outside formal governance, it creates what I call invisible risk. The change might work technically, but it's an architectural failure. Here's a scenario I've seen too often. An engineer writes a script to fix a recurring issue. It works perfectly. They share it with the team. Soon, 20% of network changes are happening via this script. But because the script isn't integrated with the company's ITSM tool, like ServiceNow or Jira, those changes don't exist in the official record. When a major outage occurs, the incident response team is looking at official records that are 20% inaccurate. They make decisions based on false data, extending the outage and increasing the cost to the business. The solution: the governance pipeline. In a professional architecture, we don't bypass change management, we automate it. We build a governance pipeline where the system itself ensures compliance. The change ticket gate. The automation engine is programmed so it literally cannot run unless it is provided with a valid, approved change ticket number. It connects to the ITSM tool, verifies the ticket is approved for now, and only then proceeds. The pre-flight evidence. Before a human even approves the ticket, the automation generates a pre-flight report. This shows exactly what commands will be run and what the expected outcome is. This gives the approver real data to look at, rather than just trusting a text description. The permanent audit trail. Once the change is made, the system automatically attaches the results, logs, before and after snapshots, and timestamps directly to the change ticket. Why this saves money. Manual audits are incredibly expensive. I've seen teams spend 3 weeks gathering data for a single regulatory review. With an automated governance architecture, that same audit takes 5 minutes. You just export the report that the system has been building automatically with every single change. Takeaway: if you can't prove who approved it and what happened, you shouldn't be doing it. Hard rules to take forward. Integrate, don't bypass. The pipeline must verify approved change tickets before executing. Answer 4 questions. Every change must answer who approved it, what was intended, what was executed, and what was the outcome. Logs are compliance evidence. Store them in tamper-proof systems with the same rigor as financial records. Preview before approval. Attach executable evidence to change requests so approvers see exactly what will happen. Automatic rollback. If post-change checks fail, the system must revert automatically. Limited credentials. Execution layers receive temporary equipment-specific credentials that prevent scope creep. Total coverage beats sampling. Govern the architecture, not individual changes. Test the reversal. If you haven't tested rollback, you don't have rollback. If you finish this chapter believing that governance is something you bolt on after building the technical components, you fundamentally misunderstood enterprise automation. Governance isn't a constraint. It's the reason executives, regulators, and auditors allow you to automate critical infrastructure in the first place.
Governance is the foundation of trust. When you build a system that proves its own compliance, you remove the fear that keeps many organizations stuck in manual processes. If you have ever been through a difficult audit, you know exactly how valuable this is. If you found this chapter helpful, please subscribe and leave a comment. I would love to hear your thoughts on automating change management. In the next 2 chapters, we are going to look at the unique challenges of working in government and critical infrastructure environments. I will see you there. Brandon, here with the second last chapter. We are wrapping things up by looking at the highest level of automation maturity. When you work in government or critical infrastructure, the rules are different. It is not just about making the network work. It is about proving that every single action followed the law. Archird is going to explain why an unprovable system is a failed system, and how to build for the strictest regulations in the world. Let us finish strong.
Chapter 10: Security, SOCI, and Government Constraints. Automation does not seek to bypass regulation. It seeks to make compliance a programmable outcome. In a regulated environment, an unauthorized script is a security incident waiting to happen. The unprovable system problem. I've reviewed automation systems at critical infrastructure sites that were technically sophisticated but operationally illegal. They could set up networks faster than any manual process, but they couldn't prove who approved the change, couldn't demonstrate separation of duties, and couldn't show that unauthorized access was prevented rather than merely discouraged. The first time a regulator reviewed these systems, they were shut down. Not because they were unsafe, but because they were unprovable. In regulated environments, a capability you cannot prove is a capability you do not possess. This chapter addresses the hardest constraint in enterprise automation, satisfying strict regulatory requirements whilst maintaining the speed of code-driven infrastructure. If you finish this chapter believing that compliance is something you add later, or that security is separate from architecture, you'll build systems that fail their first regulatory review. The regulatory reality. For organizations operating critical infrastructure, power grids, telecommunications networks, financial systems, government services, the operational bar isn't merely high, it's absolute. The Security of Critical Infrastructure Act, along with various government cybersecurity frameworks, demands more than just good security. It demands verifiable resilience. In these environments, your architecture must address three specific challenges. The insider threat constraint. The system must technically prevent a single person from making a significant change alone. This is often called two-person integrity. Your code repository and your deployment pipeline must be configured so that one person writes the code and a different authorized person approves it before the system can execute. The sovereignty constraint. You must know exactly where your data and your management systems live. In many government contexts, using a public cloud service to manage a private power grid is a violation of national security policy. Your architecture must be able to run air-gapped or within strictly controlled local environments. The immutable audit constraint. It is not enough to have logs. Those logs must be stored in a way that they cannot be altered, even by the person who has God mode access to the network. This proves to regulators that the history of the network hasn't been tampered with to hide a mistake or a breach. Compliance as code. The secret to succeeding in these environments is to stop treating compliance as a manual paperwork exercise. Instead, you turn the regulations into automated tests. If the law says all changes must be approved by a level 4 manager, your Python code checks the digital signature of the approver against the company's HR database before it allows the change to proceed. If the signature doesn't match, the change is blocked. You haven't just followed the law, you've made it impossible to break it. Takeaway. In critical infrastructure, the goal isn't just to automate the network, it's to automate the evidence of compliance. The core principles of this book. These principles form the foundation of enterprise network automation. They're not negotiable in regulated, high-stakes environments. Architecture trumps tooling. Select the layers and connections first. Select execution engines second. Tools implement architecture. They don't define it. Version control is the source of intent. If it's not in the repository, it didn't happen. The repository is the authoritative record of what the network should be. Control layer is the enforcement boundary. Use Python to validate, gate, and coordinate every change. The control layer prevents invalid changes from reaching production. Governance is a feature, not a constraint. Auditability is the product of automation. Build traceability, approval verification, and rollback capability into the architecture from the beginning. Safety is the metric. Success is measured by safe-to-fail reliability, not by speed or automation coverage. Trust is built through graceful failure, not perfect execution. If you finish this book believing that automation is primarily a technical challenge, you've missed the fundamental lesson. Automation in critical infrastructure is an organizational capability that must be designed for longevity, governance, and resilience. Build platforms that will outlive their creators. Design architectures that will survive tool migrations. Create capabilities that regulators can audit with confidence. This is enterprise automation.
We have reached the end of the second last chapter, through network automation architecture. I hope these chapters have given you a new perspective on how to build systems that are not just fast, but safe, governed, and truly professional. Remember, the goal is to build something that outlives any single tool or person. If you enjoyed this series, please make sure to subscribe and share it with your colleagues. Thank you for listening, and I will see you in the final chapter. Brendan here for our final chapter. We have covered a lot of ground, from the technical structure to the governance of automation. But as we close out this journey, we have to talk about the most important part. We are talking about building a practice that it is one thing to write great code, but it is another thing entirely to build an organizational capability that survives change, turnover, and time. Archird is going to help us bring all these principles together into a final blueprint for success. Let us join Archird for the final chapter.
Chapter 11. Capability, not just code. Building a sustainable practice. Automation is a journey, not a product. Success is not measured by the number of scripts you have, but by the number of manual tasks your organization no longer fears. When good code isn't enough. I've reviewed automation programs that possessed impressive technical capabilities, but collapse within 18 months of deployment. They could set up network segments across 500 switches in minutes. They could generate configurations for complex routing policies automatically. They could connect with a dozen different vendor systems. Yet, they failed. The failure wasn't technical. The code worked, the connections functioned, the performance was acceptable. The failure was structural. These programs had no repeatable processes, no clear ownership model, no succession planning, and no mechanism to evolve as requirements changed. When the original author left the organization, the automation stopped. When business requirements shifted, the system couldn't adapt. When an audit demanded proof of governance, there was none to provide. The technical sophistication was irrelevant because the organizational capability didn't exist. This chapter brings together the architectural principles from throughout this book into a blueprint for building automation programs that survive organizational change, regulatory scrutiny, and the inevitable departure of their creators. If you finish this chapter still believing that automation is a technical challenge rather than an organizational transformation, you will build systems that eventually fail. The 5 foundations of lasting automation. A resilient enterprise network automation capability rests on 5 foundations. These are load-bearing structures. Remove any one, and the entire system eventually collapses under the weight of organizational complexity. 1. Architecture before tooling. The most common mistake is tool-driven design, selecting a product and then designing processes around its specific features. This produces systems locked to one vendor that are impossible to replace when the tool inevitably fails or is discontinued. The correct sequence is to define your architectural layers, establish governance boundaries, and specify your integration points first. Only then should you select execution engines that fit that architecture. When your chosen tool reaches end of life, your architecture protects you from having to rebuild your entire business logic. 2. Testing in reality. Code that hasn't been tested in a production equivalent environment doesn't belong in production. This requires physical and logical separation of environments, sandbox, staging, and production, accurate simulation of production topology, and a sequential progression where no shortcuts are allowed. Your test results are meaningless if your staging environment doesn't reflect the messy reality of legacy hardware and software versions found in your real network. 3. Security as code. Policy documents don't enforce security. Code enforces security. This means moving to policy as code, where policy regulations become automated validation checks, and regulatory frameworks like SOC become architectural constraints. When an auditor asks how you ensure compliance, you don't show a policy document. You show the code and the immutable test results proving it works every single time. 4. Connecting to the business. Automation that doesn't connect to operational systems is shadow IT. It must speak the language of the organization by connecting to change management, ITSM, monitoring platforms, and asset databases. This connection ensures that every automated change is authorized, visible, and recorded in the official systems of record. 5. Surviving staff turnover. The bus factor is the number of people who would need to be hit by a bus before a project becomes unmaintainable. For many automation projects, that number is 1. Lasting automation requires documentation that explains the why behind decisions, code that is readable by others, and team ownership, where at least 3 people are familiar with the system. Knowledge concentration is organizational fragility. The cultural shift. The hardest part of building lasting automation is the mindset shift required from the entire organization. For engineers, you must move from configuring equipment to designing the systems that configure equipment. For managers, success is no longer measured by how many tickets we closed, but by how many manual tasks your organization no longer fears. For organizations, networking must move from a reactive cost center to a programmable asset that enables business agility. The regulatory reality. In the context of the Security of Critical Infrastructure Act, manual network management is increasingly seen as a regulatory risk. Regulators expect traceability, provable access, and automated compliance. Automation is the only viable path to compliance in modern critical infrastructure, but it must be done with architectural discipline. An unprovable system is, from a regulatory perspective, a failed system. The core principles of this book. These principles form the foundation of enterprise network automation. They're not negotiable in regulated, high-stakes environments. Architecture trumps tooling. Design the layers and connections first. Select execution engines second. Tools implement architecture. They don't define it. Version control is the source of intent. If it's not in the repository, it didn't happen. The repository is the authoritative record of what the network should be. Control layer is the enforcement boundary. Use Python to validate, gate, and coordinate every change. The control layer prevents invalid changes from reaching production. Governance is a feature, not a constraint. Auditability is the product of automation. Build traceability, approval verification, and rollback capability into the architecture from the beginning. Safety is the metric. Success is measured by safe-to-fail reliability, not by speed or automation coverage. Trust is built through graceful failure, not perfect execution. If you finish this book believing that automation is primarily a technical challenge, you've missed the fundamental lesson. Automation in critical infrastructure is an organizational capability that must be designed for longevity, governance, and resilience. Build platforms that will outlive their creators. Design architectures that will survive tool migrations. Create capabilities that regulators can audit with confidence. This is enterprise automation.
We have reached the end of our journey through network automation architecture. I hope these chapters have given you a new perspective on how to build systems that are not just fast, but safe, governed, and truly professional. Remember, the goal is to build something that outlives any single tool or person. If you enjoyed this series, please make sure to subscribe and share it with your colleagues. Thank you for listening, and I will see you in the next project.